So electron energy and position are complementary. We were just talking about velocity and position, but the kinetic energy is equal to 1/2 mass times the velocity squared. So for an electron with a given amount of energy, the best we can do is describe a region, a probability distribution map where that electron is likely to be found in the atom, and that is called an orbital. Orbitals are different than orbits. Orbits are like what the Earth does around the sun. The Bohr model, the electrons were orbiting the nucleus. That was all nice and familiar. Unfortunately, it's also wrong. So here we have orbitals. And we do find that many of the properties of atoms are related to the energies of the orbitals, of the electrons. So Schrodinger, this is the same guy with the cat experiment. This is very simple representation of Schrodinger's equation. It allows us to calculate the probability of finding an electron with a particular amount of energy at a particular location. The math here is beyond me. No, thank you. So solving this equation gives not like single answers, numbers, but gives us wave functions. The wave functions, and those describe the wave-like nature of the electron. And so if you plot that wave function squared, that represents an orbital. So it turns out that size, shape, orientation of the orbital depend on 3 integer terms in the wave function. And those are called quantum numbers. And those were put in there because we know that the energy of electrons is quantized. So the quantum numbers have names. There's the principal quantum number, N, the angular momentum quantum number, which is L, the magnetic quantum number, M sub L, and then there's a fourth one, the spin quantum number, M sub S. So the principal quantum number is, you can think of it as being a lot like the levels in Bohr's model, where n equals 1, n equals 2, n equals 3. The higher you go, the more energy it has. N can be any integer greater than or equal to 1. 1, 2, 3, 4, 5, 6, 7, whatever. Larger n, higher energy, larger orbital size. For hydrogen, the energy of an electron is equal to negative 2.18 times 10 to the minus 18th joules times 1 over n squared. That's that principal energy level. The energy is negative because the electron's energy is lowered by its interaction with the nucleus. N gets larger, the energy differences between the orbitals get smaller. So this is the energy at different principal energy levels. So this is the first one, negative 2.8 times 10 to the minus 18. And then n equals 2. This is higher in energy. I'm sorry, I'm having a brain fart. Yeah, okay, it's because of the negative sign. So this is negative, and as we're getting up, we're getting less and less negative. We're getting closer to 0, which is getting bigger, right? Oof. So as n is bigger, the energy of the electron is higher. Higher energy is unstable, right? But also look at the difference between level 1 and 2 is really big. The difference between 2 and 3 is smaller. Between 3 and 4 is even smaller. And as you go out, the difference between the levels gets smaller and smaller. So that's the principal quantum number. The angular momentum quantum number determines the shape of the orbital, and there are certain values that L can have. It can be 0 up to whatever n is minus 1. And each of these values has a letter designation, S, P, D, and F, and those came from words that were descriptive of spectral lines. That's why it's not A, B, C, D, it's S, P, D, and F. So if we have L equals 0, that's S, just because it is. Okay, so what values of L are possible for n is equal to 3? Well, L is 0 up to 1 minus n minus 1, sorry. And it's integers. So if L is equal, if n is equal to 3, right, then 3 minus 1 is 2, right? So L can be integers from 0 to 2, which would be 0, 1, and 2. Does that make sense? So that'll be this guy. So 0 corresponds to S, 1 corresponds to P, and 2 corresponds to D. Magnetic quantum number specifies the orientation in space. And the direction in space is just relative to other orbitals. They don't all line up vertically or something. And these values go from negative L to positive L, including 0. There's questions on the worksheet about this. I don't like questions like this on an exam, but I do have to teach you this stuff. So if L is equal to 2, then M sub L can go from negative L to positive L. So negative 2 to positive 2, including 0. So minus 2, minus 1, 0, plus 1, plus 2. So those are describing orbitals, and there's five orbitals with L equals 2. I just feel like I'm Charlie Brown's teacher up here right now. Blah, 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 blah. So if L is equal to 2, what values of M sub L are possible? Well, that's dumb because it was just in the previous slide, right? It's this one. I should change that. Spin quantum number talks about the spin of an electron. So electron spin is a fundamental property. They're not actually spinning like tops, but I give you permission to think of them that way because it's so much easier. So just like Beyblade tops, some of them spin clockwise and some spin counterclockwise, right? Electrons are like that, but we call their spin up or down. M sub S is not an integer, it's 1/2, either plus 1/2 or minus 1/2. So you could either have spin up plus 1/2 or down minus 1/2. So if we combine these different quantum numbers, they describe a single electron. If we look at the first 3, they describe an orbital. So you could think of this as being a little bit like the Social Security number for an electron. Each electron in an atom has its own set of quantum numbers. So if we're looking at orbitals that have the same value of n, we say they're in the same principal level or principal shell, and it's kind of like that orbit in Bohr's model. And then there are sublevels or subshells. So in the first principal energy level, there's only one value of that angular momentum quantum number, L equals 0. So there's one sublevel. And then m sub L can only be 0, which is s. And so we've got the 1s orbital. In the second level, we've got two different sublevels, L equals 0 and L equals 1. When L equals 0, we always just have one orbital. L equals 1. Now we've got -1, 0, and +1, so we get 3. Third level has 3 sublevels. So the first one, the second one, and the third one here with L equals 2, there's 5 different possibilities, and so there's 5 of these d orbitals. And I'll just give you a little sneak peek at my one of my favorite analogies. This is called the Quantum Hotel. It's a discount resort for electrons. So I think of this as being like a hotel. So this is the first floor, the second floor, and the third floor. And this is, the sublevel is a room, and the orbital is a bed. And so on the second floor, you've got 2 rooms. The first room has 1 bed, the second room has 3 beds. The third level has 3 rooms. The first one has 1 bed, and we've got 3 beds, and then we've got 5 beds. On the fourth floor, we have 4 rooms. 1 bed, 3 beds, 5 beds, and a room with 7 beds. Kind of crazy. But that would have been cool when we were traveling with 6 kids, because they could each have their own bed. That would have been really awesome. List the quantum numbers associated with all of the d orbitals, the 5d orbitals. Okay, so 5 is that principal quantum number. So n equals 5. And d, there's s, p, and d. S is 0, p is 1, d is 2. So that means that L is equal to 2. And then m sub L, what are the possible values for that? Yeah, -2 to +2. So how many 5d orbitals exist? There are 5. They all have the same n and the same L, and it's the third number that tells them apart. So those are the orbitals, like the beds. The fourth quantum number gives us the spin of the electron. In the quantum hotel, I make that into, are you sleeping right side up in the bed or upside down in the bed? And we'll get to that later. So this could have, we could put 10 electrons in here, but there's 5 places. I don't want to do that one. So each wavelength corresponds to an electron transition. If the atom absorbs energy, the electron goes to a higher energy state. It's excited, because when we have more energy, we're excited, right? But that's unstable, and it comes back down to the lower energy state. And when it does that, the difference in energy is released as a photon of light. So that's what's happening here. The ground state, this would be for hydrogen with 1 electron. So the first electron is usually in this lowest energy state. And then it will go, it can absorb energy and go up to a higher level, but it won't stay up there. It'll jump down. It could jump down to 2, or it could jump all the way to 1. And then it's going to release the energy as a photon of light. So these transitions is like riding the bus. You have to have exact change, right? It's kind of crazy. I haven't ridden the Fresno area bus, but a lot of buses, they won't take more. You have to have the exact right amount of money. Why won't you take more? But anyway, this is like that. If you have too much energy, the electron just won't absorb it. It's like, no, I have to have the exact fare to one of these other levels, otherwise nothing's going to happen. So the high energy states are unstable. They tend to lose energy and go back to lower energy states, and each line in the spectrum corresponds to a difference in energy. So we can predict the lines of hydrogen. And the Bohr model and quantum mechanics work for this one because we just have the one electron. So the energy of the photon released equals the difference in energy between the two levels. So the final level minus the initial level, because delta is always final minus initial. So we learned that the energy of an electron in hydrogen is equal to negative 2.18 times 10 to the minus 18th joules times 1 over n squared. So here it's the final n squared, and then we're subtracting the energy at the initial n squared. So that can be simplified to this equation, which you will use on the worksheet. So this is kind of, I find this sometimes hard to remember or confusing. So the change in energy for the atom is negative, the opposite in sign to the change in energy, the energy of the photon. Because one's going out and one's coming in, essentially. Wavelength is equal to hc over the energy. That's just a rearrangement of E equals hc over lambda. So these are the electron transitions for hydrogen. These are larger transitions, higher energy, so they're ultraviolet and we can't see them with our eyes. These are the visible light ones, and they're all going from, there's from 5, 4, or 3 down to 2. And then there are other ones that are smaller, but those are infrared and we can't see those either. Now this is the kind of question that could show up on an exam. Which transition emits light with the shortest wavelength? Well, what we learned is that these changes here relate to the energy, right? So the shortest wavelength, are we looking for the highest energy or the lowest energy? The highest. Because the short wavelength was higher energy. So we're looking for the highest energy. So we've got from 5 to 4, from 4 to 3, from 3 to 2. The levels go like this. They get closer and closer together. So which is the bigger one? It would be this one, right? The one that's lower numbers. These are all a transition of one quantum number. So this would be the highest energy, the shortest wavelength. And then sometimes the questions will be kind of tricky because they'll also give you like n equals 1 to n equals 2. You're like, oh, well, the difference in energy between 1 and 2 is bigger than between 2 and 3. But does this represent energy being emitted from the atom? This is going up in energy. This is the atom absorbing the energy. So you have to watch out for that. Determine the wavelength of light absorbed when an electron in a hydrogen atom makes a transition from an orbital in which n equals 2 to one in which n equals 7. So n equals 2 from this one to that one. Which is the final? 7 or 2? 7. And which is the initial? The other one, 2. Okay? So let's go back and look at that equation. So negative 2.18 times 10 to the minus 18th joules times 1 over nf squared minus 1 over ni squared. Final minus initial. So the change in energy is equal to negative 2.18. Check my, is that 18? Thank you. Joules times 1 over the final F, 7 squared, minus 1 over the initial F squared. And, you know, don't try to do anything silly with fractions here. Just let your calculator do this. Negative 2.18 EE minus 18 times, open the parentheses, 1 divided by 7 squared, minus 1 divided by 2 squared. Close the parentheses. .01 times 10 to the negative 19th joules. That's the energy. How do we find the wavelength? Yeah. So the energy equals hc over lambda. So we end up with lambda equals hc over the energy. 6.626 times 10 to the minus 34 joule seconds times 3.00 times 10 to the 8th meters per second divided by 5.01 times 10 to the minus 19 joules. 6.626 EE negative 34 times 3 EE 8 divided by 5.01 times 10 to the minus 19. So this is 3.97 times 10 to the minus 7 meters. Any questions? That's not what I meant to do.